This is sections 9.4, comparisons of series. So in this section, we will continue to develop some quick tests to determine whether a series converges, diverges. Let's do a quick review here. If we have the series 1 over n squared, it's an n from 1 to infinity. So does the series converge? Not. Well, you recognize that this series is what is a special type of series here. What is it called? P series. Okay, remember this one is a P series, and the P series, again, we need to have the explanation here. The P series with P equal 2. So this series, we should know it's actually converges. It converges, okay? If we write it out explicitly, it is 1 over 1, right? It's 1 over 4 plus 1 over 3 squared 9 plus 1 over 4 squared 16, and so on. Right, so this series, we know the answers, okay? So that is a P series, so it converges. Now suppose you are asked to determine whether this series here converges 1 over n squared plus 3. Okay, now you should notice that in this case, it's not P series anymore because you have extra terms at the bottom. And if you're going to write down explicitly, I think it's going to be 1/4 here. There's 2, right? So it's going to be 1/7. If it's 3, it's the 1/12. And it's 4, so we 1 over 19, and continue. Now see, if we're going to test this series directly, I don't know, right? So I don't know whether it converges or not. But if you compare this series with the series that we know, what do you see? Formula, it's the same with the 3 extra. So that's why I see here, it's 1 is 4, 4 is 7, 9 is 12, 16, 19. When you compare term by term, the denominator here is always adding 3, right? You get the other denominator, okay? If you compare term by term, which one is bigger, which is smaller? You see that 1/4 smaller than 1, right? 1/7 smaller than 1/4, 1/12 smaller than 9, and 19 over smaller than over 16. So every single term in this red series that we want to test is always smaller than this series here. Every term, I mean, I should say, the corresponding term in the blue series. The reason, if you look at the formula, right, we have 1 over n squared plus 3, and then the blue series has a formula as 1 over n squared. And then you're like, okay, so which one is bigger? Well, 1 over n squared is always bigger. Well, the smaller, right? 3 is always the 3 units more than this denominator, so make it smaller. So what we know is every single term in the red series is smaller than every term in the blue series. Now, we know that this series converges. What it means is the sum has to be finite, right? I don't know what's that, maybe 20, 30, 10, or whatever. It has to be finite. What do you think about this sum? But this one is finite. So that means this sum has to be finite or it has to be smaller than the series. Because all the term here is smaller than all the terms in the blue series, the sum has to be less than the sum here, and therefore the red series must converge. Okay, so that is really what we call the comparison test. That's one direction. Now, so let's do it in general here. Again, the idea is when we do the comparison for non-negative series, again, that only works when you have non-negative terms. You don't want to have negative positive. It's going to make things complicated because the sum is going to be going back and forth between positive and negative. If we have non-negative terms here, say all positive, if every terms of the series is less than the corresponding terms of a convergent series, right? So what I mean is, if we have this red series, we have the blue series. If the red series converge, okay, so if that is converge, okay, then the blue series is one smaller, like below, then this series must converge because the sum is smaller. Okay, so if the larger series converges, the smaller series converges. When I say the smaller series, I mean a series with the corresponding term smaller than the other series. Okay. Now, the other directions also work, but you would be careful with the exact direction here. If I have every term of a series is greater than the corresponding term of a divergent series. Okay, so again, let's say I have the red series, I have the blue series, and then the red series. The blue series have the term, all the term is bigger, right? So right above. If this red series converge or diverge, I mean that diverges, so does the blue ones. Again, the reason is because if this red series diverge, that means sum of all these terms is huge, approach infinity. But then the sum of these series must be larger, so it can approach infinity as well, and so it diverge. Okay. Now let's do it. Put it in a very formal term. This is called the direct comparison test. Suppose you have a series where the a sub n less than or equal to b sub n for all n. It's bigger than 0, so make sure that all the term has to be positive or the 0. Now, if b sub n, the series converges, that means this side, if the larger size, the larger series converges, then the smaller series on this side converges as well. Or if we know the smaller size here is a sub n diverges, then this larger series diverges as well. Okay. Now, in order to use this test, you see that you have to figure out how to compare the series we are testing with a series that we know. Right? So one series given, one series need to find. So to find that known series, we often use or compare that to the P series or geometric series, so those series that we know whether they are convergent or not, right? Now, using this direct comparison test, you got to be careful with the directions of the comparisons, greater than or less than. I'm gonna come back to this statement next slide, but gotta be careful with the sign of the inequality. For example, let's test the series here. 1 over n squared plus 1 and from 1 to infinity. And what we do is, okay, so we have a series, right? We want to know the answer. And to do that, we're going to compare that series to a known series. Right, so how do we come up with the series to compare with? Here's what we're going to do. When you look at the general terms, so we're going to have always have fractions, okay? You will keep the dominant terms of the numerator as well as the denominator. That means you're going to eliminate all the terms by keeping only one leading term. So in this case, again, let me call this is we'll call it A sub n and B sub n. Let's say this is your A sub n, and to come up with the series to compare with, I call B sub n. Now look at the numerator, it's only one term, so I have no choice, gotta be 1. The denominator has 2 terms because n squared is much bigger than 1. Since n goes to infinity, you drop the 1, that's the n squared. Right, so basically I'm comparing these two series. Now first, I noticed that 1 over n squared plus 1 has to be smaller than 1 over n squared, right? The denominator here is larger, so fraction is smaller. So that has to be smaller than that. And once you got that, then I'm going to test the series that we found, or we come up with. Let's consider converge or diverge. Well, this one converges because why? Because 1 over n squared is a p series with p equal 2, right? It's bigger than 1. So I know that the series here converges. Now, since the series converges, the original series we test 1 over n squared plus 1, and from 1 to infinity must converges as well, right, by the direct comparison test. Okay, can you see that? Now, sometimes it's a bit harder to compare when you have n's and numerators as well as the denominator. Okay, so one thing you can do is when you have more than one term, you're going to drop the insignificant term, like they dropped 1 here. Okay, so even though if you have a series like this, say 4 over n squared even plus 3n, I can still do the same. So basically you drop the 3n. 3n is smaller than n squared and n is large. So if you drop 3n, it's left with 4 over n squared, and then compare these two to see which one's bigger. So I guess this size is bigger because you have a larger denominator here. So you're gonna come up with this. Okay, compare, test this series, and then conclude about the series. So some other things that might help you determine which series you come up with is, besides the way I just show you, keeping the dominant terms, if you see a series that has psi particular. Right, so let's say if psi over 3n, and then with this the same series, I'm going to look at n squared plus 6. Notice that when you compare, the denominator is actually still the same. You just drop the 6, and then it's going to be over n squared. Knowing the denominator is bigger, so it should make the fraction smaller. But the numerator, how do we do? Whenever you see the sine, the cosine, or tangent, so those are the unwanted term. Or you can even have natural log in it, okay? But then we can compare this with what do we know? Sine theta is always less than equal to 1. Cosine theta is same thing, less than equal to 1. Now, natural log of x, say, it's a bit hard to determine whether it's comparing to which constants. But if you recall, the natural log would go like this. And essentially, since it's getting slow, going to increase the slow pace, it's definitely smaller than the 45-degree line here, right? So x. So in other words, what I'm saying is the natural log of x, this function has to be smaller than the line functions, y equal x. So we always have natural log of x less than equal to x. And then we're going to use this three to compare. Okay, for example, right here, I don't care what I have inside, but side of any quantity, you know that the side of it's always smaller than 1. Right, so that's smaller than 1. And then from here, we make the same conclusions here. So that's converges, okay, because 1 over n squared, p equal to greater than 1. Because that one converges, then so either problem means they must converge as well because it's smaller, they have smaller sum. Okay. Now, if you look at the example here, that one's a bit tricky. If we're gonna come up with something to compare, and like I told you, this is really a fraction, so this denominator stays the same. Now the numerator, I have two terms. Which term is more dominant? Don't forget the exponential function is growing to infinity really quick. That's more dominant. That means I drop the n, and I have 2 to the n over 3 to the n. And ask myself, what do we know about this series? Okay, what do we know about the series? Well, if you look at it carefully, you write down explicitly as 2 over 3 plus 2 squared over 3 squared plus 2q over 3q. Now, do you notice that this is really a geometric series? I time 2/3 to get the next term. So the series is geometric series. And what's a common ratio? The common ratio here is c times 2/3 to get the next term. So it's 2/3 smaller than 1. And because smaller than 1, then the series here converges. And since it converges, I can tell you that the original series at the beginning also right, so take it back. I almost fall into the trap that I'm trying to warn you. There's an issue here. First, I haven't compared yet. What I'm just saying is in this series I'm comparing converges. But turn by turn, which side is bigger. Okay, so what I mean is if you look at 2 to the n plus n over 3 to the n, and 2 to the n over 3 to the n, which terms are bigger? Well, the denominator is essentially the same. The numerator here has an extra n compared to this side, so you have this inequality. Now, it would make this hard to do because since the size smaller, remember that is the side we want to make sure it follow. You look at this 2 to the n over 3 to the n, right? So this numerator is smaller than that numerator because that has extra n, right? That's smaller. As soon as smaller, and we know the series converges, right? So the smaller converges. What about the series test? Does it converge? Well, yes, we don't know because now the series testing on the larger side, So I don't know about this sum. This sum may go to infinity. It could be divergence. Could be a convergence. We don't know. So in this case, it's actually failed. We want to have the inequality facing this way, so that if the large converge, the smaller converge. But unfortunately, the inequality is not satisfied, right? So it's going to be the other way around. So this series, I cannot use direct comparison. Actually, there's a trick to do it, but it's going to be very difficult. So what I'm going to do is we're going to use another type of series or test called limit comparison. We still come up with a series as before, right? So let's say this is your A sub n, that's B sub n. Now, for direct comparison, you are doing basically take a difference of the two terms to see if it came out to be a positive. Then you know that it's this side is always bigger than that side, and etc. So one way to compare is compare directly, take a difference. Another way to compare them is, sometimes we say, the height of this tree is 3 times the height of that tree. So you see, in that statement, we are not comparing directly, like absolute difference, how tall one tree compared to the others, but we're going to compare in terms of number of times. Or in other words, when I give you two numbers, say 6 and 2, right, you can say, well, the difference is 4. So 6 is 4 units bigger than 2. Or we can compare it by forming the ratio, 6 over 2. So if you take 6 over 2, you got 3. Then we say, that this number will be 3 times as big as this number. Right? So we're going to compare by forming the ratio. Okay, so that leads to what we call the limit comparison test. Right, so here is the limit comparison test. Now, in limit comparison test, we have A sub n bigger than 0, B sub n equals 0. I would like to read that, so we're gonna stop here. This first part, we're gonna move on. Talk about this in the second part.